Welcome to Spring LIB.
So anytime we're going to do any kind of optimization problem, especially if it's like geometric in some sense, I like to draw a picture. So the way they kind of have this set up is, so they say they have some fencing, and then they're going to run a fence in between, like the fencing in the middle, kind of parallel, like how I have this drawn here. And now what we want to do is find some way how we can minimize this cost while having a fencing of or a area on the inside here of 1.5 million square feet. And actually, let's just go ahead and write this out without the whole million thing. So it'll just be 1500. Okay, so we have this here. Well, if we were to think about this now, we're essentially just wanting to minimize our perimeter of this. So now I'll call these x's here, and then I'll call just like the top and bottom y. So our perimeter right now of this in total is going to be 3x plus 2y. But since this is in two variables, remember we're going to want to find some way to rewrite this so we just have one variable so we can take the derivative. And over here, this area we're working with should be equal to, well, it's just the side length of the outer rectangle times the other side length of it. So it'll just be x times y. And so I'll just go ahead and solve for y. So that would give us y is equal to 1.5 million over x. And then we can come over here and plug this in for y. Okay, so we're going to end up with, so p is equal to 3x plus, so 2 times that, so that's going to be 3 million now, all over x. And now we can go ahead and take the derivative of this, since this is in terms of only x now, so this is our perimeter function in terms of x. And this is assuming like the cost doesn't really matter since we're using the same kind of fencing for everything. So yeah, if we just use less of it overall, then we should just spend less as well. Yeah, so now we want to try to take the derivative of this so we can try to minimize the function. So the first thing we need to remember, this is really here x to the negative 1. So when we take the derivative of that, so p prime of x, that would give us, so 3, then minus 3 million over now x squared, because power rule, remember, says take this, move it to the front, subtract 1 off. And what we want to do is set this equal to 0. So I'll go ahead and multiply everything by x squared. So it would be 3x squared is equal to 3x squared minus 3 million is equal to 0. Then we can add 3 million over, divide by 3. So that gives us x is equal to 1 million. Yep, that's the correct number of zeros. And then we can take the square root on each side. And so that would give us x is equal to plus or minus 1,000. But in this case, it wouldn't make sense for us to talk about a negative side length. So we just throw that out and we have the positive 1 now. Okay. And at this point, we can go ahead and plug this in to one of our equations so we can figure out what the other side length is going to be. All right, so over here, we can just plug that into our constraint equation. So we now take this, plug in 1,000 there, so that'll give us y is equal to 1.5 million divided by 1,000. So we essentially just cancel out 3 of these zeros for each. And so then that tells us y is equal to 1,500. Oh, and both of these should be in feet, by the way. So if we were to kind of draw this again and look at what our dimensions should be, so we should have where our top ones, so going across here like this, is going to be 1,500 feet. And then the three sides are going to be 1,000, because if we come up here and look at this again, it was x, 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 and then y, y. So I guess we can kind of write this out. So we want three sides with 1,000 feet and two sides with 1,500 feet. So these would be the dimensions we would need in order for us to minimize our total cost.